In the name of God, hello everyone. This is Fatemeh Sousani, a PhD candidate at Sharif University of Technology from Iran. It's my pleasure to have the opportunity to participate in this prestigious conference. And my presentation title is Enhancement of Photocatalytic Capability of Graphite Carbon Nitride by Heterojunction Creation aiming hydrogen evolution via water splitting. Depletion of fossil energy resources, environmental pollution, and the rapid development of renewable energy sources have become pressing concerns. Solar-driven photocatalytic hydrogen evolution is gaining prominence as a sustainable and environmentally friendly alternative to fossil fuels. In the past few decades, various semiconductor photocatalysts have been developed, but their efficiency under visible light remains a significant challenge. Graphite carbon nitride is gaining significant interest due to its responsiveness to visible light, cost effectiveness, easy production route, low toxicity, and excellent stability. However, it shows some drawbacks, including low density of reactive sites, low specific surface area, fast recombination of electron hole, non-recyclable that show low efficiency under visible light, and some methods have been improved to increase the efficiency of graphite carbon nitride, including creating heterojunction that separates electron hole recombination rate. Based on this consideration, in this study, NiCO-ZnCdS g-C3N4 ternary nanophotocatalyst was synthesized through a simple hydrothermal method. And as expected, this ternary nanophotoCatalyst exhibited remarkably enhanced photocatalytic efficiency for hydrogen evolution rate. This figure showed a schematic illustration of synthesis of the sample. According to figure A, graphite carbon nitride was synthesized through a simple thermal polymerization method. According to figure 1, in detail, 10 grams of urea was heated from room temperature
Returning visitor
550 Celsius degree with the rate of 2.5 Celsius degree per minute and then a natural cooling. According to figure C, ZnCdS was synthesized through a hydrothermal method from the zinc acetate, cadmium acetate, and sodium sulfate as precursors. According to figure C, NiCO-ZnCdS was synthesized according to the figure from previously synthesized ZnCdS and nickel nitrate, cobalt nitrate, and NaBH4 as precursors. And finally, the ternary nanophotocatalyst was synthesized from previously synthesized g-C3N4, NiCO-ZnCdS, and with a simple hydrothermal method according to the figure D. The sample was characterized and analyzed with FESCM, XRD, BET, UV visible, DRS, and PA. This figure showed the experimental setup for photocatalytic hydrogen evolution. According to the figure, photocatalytic hydrogen evolution experiment was carried out in a quartz reactor and under visible light radiation provided with an LED lamp. And according to the figure, in detail, 100 milligram of photocatalyst powder was dispersed into the 100 milliliter of aqueous solution of triethylenolamine as sacrificial agent. And then before the reaction, to eliminate the dissolved oxygen, the reaction, the reactor was purged with nitrogen gas, and then the suspension was magnetically stirred and exposed to the light irradiation for 4 hours. And the gas samples were collected and injected into the gas chromatography each hour. And then the amount of hydrogen was detected and quantified. This figure showed the FESCM analysis and image of the prepared sample. According to figure A, g-C3N4 shows a layered and porous structure. The porous structure is due to the formation of gas bubbles during the thermal treatment of g-C3N4. According to figure B, ZnCdS shows irregularly nanoparticle with an average size of 47 nanometer. And according to figure C, both curved layer of g-C3N4 and ZnCdS nanoparticles are evident. And however, because of the minimal amount of NiCO nanoparticles in the sample, it's hard to distinguish them in the microstructure. However, the existence of these nanoparticles was further proved by EDAX analysis. This figure shows the XRD spectra of the samples, and according to pattern A, the XRD pattern of pure g-C3N4 displayed two distinct diffraction peaks at 30.31 and 27.6 respectively. The initial weak peak, according to the pattern A, correspond to the 100 diffraction plane of g-C3N4, representing the in-plane structure repeating units of triazine, and the second peak correspond to the 002 diffraction plane of g-C3N4, which is indicative of the layered stacking of the CN conjugated system. And according to pattern B, for pure ZN-CDS, some distinct diffraction peaks are observed. These peaks are in good agreement with the cubic phase of ZNS. And according to pattern C and pattern D, for NiCO, ZN-CDS, and terminal photocatalyst, no characteristic peaks for NiCO nanoparticles can be observed. This can be attributed to the low quantity and weak diffraction intensity of NiCO nanoparticles. However, NU diffraction peaks at 17.96 appears in the terminal photocatalyst pattern, which can be attributed to the 100 plane of g-C3N4. This peak shifted to a higher angle compared to pure g-C3N4. This figure shows the nitrogen absorption-desorption isotherm of g-C3N4 and terminal photocatalyst aligned with the corresponding pore size distribution shown in the inset. According to the figure, both isotherm exhibited characteristics of type 5 isotherm. This indicates that the presence of mesopores in the structure, and additionally, the isotherms demonstrate a sharp increase in adsorption in high relative pressure, indicating the presence of large mesopores and micropores. And according to the figure, the hysteresis loop shape is in both isotherm is type H3, which indicative of the plate-like particles with a slit-shaped pore. And according to inset, the pore size distribution curves reveal a broad range of pore size ranging from 2 to 100 nanometer, with the prominent peak centered at 4.6 nanometer. This further confirmed the presence of a mesoporous structure. In comparison to pure g-C3N4, nanophotocatalysts exhibited an increase in specific surface area. This increased specific surface area provided a higher density of reactive active sites for redox reaction and its advantages for photocatalytic application. This figure shows the UV visible DRS and tau pollutes of the synthesized sample. According to figure A, terminal nanophotocatalysts show a higher absorbance compared to g-C3N4 and ZN-CDS between approximately 355 nanometer and 537 nanometer. And these effects can be attributed to the formation of a direct Z-skin configuration between NiCO, ZN-CDS, and graphite carbon nitride. And this structure effectively suppresses electron hole recombination and prolonging their lifetime. This figure shows the PL spectra of the as-prepared sample. For ZN-CDS, two PL emission peaks are observed in the figure, centered at 481 and 576 nanometer. These peaks can be attributed to the zinc and sulfur vacancy respectively. In the case of terminal nanophotocatalyst, the three broad emission peaks are observed, centered at 423, 584, and 658 nanometer. The lower PL intensity of the nanophotocatalyst compared to other samples suggests that the recombination rate of the photogenerated electron hole pair is significantly inhibited. This reduced recombination rate is beneficial for achieving efficient photocatalytic performance. This figure shows the photocatalytic hydrogen evolution performance of the as-prepared sample in aqueous solution containing triethanolamine as a sacrificial agent under visible light radiation for 4 hours. It can be seen in the picture that pure g-C3N4 alone exhibited a very low hydrogen evolution rate, which is not detectable by gas chromatography. According to the figure A and red one, ZnCdS nanoparticles shows an improved hydrogen evolution rate of 535 micromole per gram per hour. However, the Turner nanophotocatalyst blue one, the figure, demonstrates the highest hydrogen evolution rate of 1,980 micromole per gram per hour, which is approximately 1,980 times and 4 times higher than that of pure g-C3N4 and ZnCdS respectively. According to the figure B at the right, it can be observed that there is a slight decline in the hydrogen evolution rate after 60 hours of radiation during the third recycling experiment. This figure demonstrates the photocatalytic mechanism of Turner nanophotocatalyst. According to the figure, a direct Z scheme forms between ZnCdS and g-C3N4. And ZnCdS, according to the figure, has a more negative conduction band, and g-C3N4 has a more positive valence band. When both of them exposed to light with energy higher than their bandgap energy, an electron from the valence band moves to the conduction band and creating a hole in the valence band. And photogenerated electron in the valence band of g-C3N4 recombine with the holes in ZnCdS. Schottky junction is formed between ZnCdS and nickel cobalt nanoparticles due to the difference in their work function, and the conduction band electrons of ZnCdS prefer to transfer to the NiCO nanoparticles, and this nanoparticle serves as electron traps, and this electron transfer reduces charge carrier recombination. And according to the figure, the electron on NiCO nanoparticles and the hole on the valence band of g-C3N4 participate in the reduction and oxidation reaction, respectively. This mechanism enhances dispersion and utilization of photo-generated charge carrier, leading to enhanced photocatalytic efficiency and effectiveness for hydrogen production. In conclusion, this Turner nanophotocatalyst exhibited a high hydrogen evolution rate of 1,980 micromole per gram per hour under visible light radiation, that's 1,980 and 4 times higher than pure g-C3N4 and ZnCdS respectively. And the results show that this nanophotocatalyst is a highly efficient photocatalyst for hydrogen evolution under visible light radiation. And at the end, in conclusion, I would like to express my sincere gratitude to all of you for being a part of this presentation today. And if you have any question, comments, or idea that you'd like to share, please feel free to reach out to me. And thank you very much.